Yeah. Hi, everybody. Hi, Virgi, and welcome to the seminar today. Our speaker is Ondřej Hulík from BUB, Brussels.
Thanks, Virginia, for the introduction and inviting me. Right, so I'm going to report on some partial progress of a project in making with a couple people from BUB, which are, maybe I should let you know, it's Dan Thompson, Alex Serran. I suppose I didn't put them in the right alphabetic order.
Could you please write it with slightly bigger letters, please?
Yes, I'll try. So this doesn't matter right now, right? But I'll do that. Writing equation.
That's fine.
Okay. Okay. And and you can hear me well, right?
Yes, you can.
So what we are trying to accomplish in this project is sort of merging two ideas. One is double field theory, and second is supersymmetric two-dimensional sigma models in one coherent picture. And so what I mean by that is, you know, maybe I should give a brief sketch. So all I'm going to talk about is two-dimensional sigma model. So my thing I'll be studying is a sigma model where I have two-dimensional source and some maps into some target space, and okay, this will be the objective. So this could be whatever dimension here right now. So these are the maps, right, of the sigma model, and there's some Lagrangian behind it. Right, and so you know these are. This is something we all know and love from string theory, right? This is the sigma model for a string, for instance, or it could be something abstract. But in particular, in string context, there's this interesting duality named or interesting symmetry named d-duality, right? And d-duality, what it does is that in its very simplest form, if there is a isometry in the target manifold, so if there's an isometry. So there would be some U1 acting on the target. So if there's an isometry, I can gauge that isometry and I can pass to some dual model, right? So maybe I'll do this picture one does that if I can start with my sigma model. So this is the action, and I have these fields phi. Then if there's an isometry, I can uplift it to this bigger model parent. Action. I gauge the isometry, so I introduce some gauge field and some Lagrange multiplier phi tilde. And then if I were to integrate out phi tilde, do people know this, or should I give an example of how this works?
Well, if you give an example, that's always nice.
Okay, then I'll maybe sketch the example. So there's a way to uplift it and then pass in the other direction to produce some dual Lagrangian, which has what used to be the Lagrange multiplier as the dynamical field, right? And this is very, I don't know, pretty mysterious thing from the perspective of the sigma model itself, because the target space of this model, it might be totally different even globally as compared to this one, right? So that's the t-duality in a nutshell. So how does that work? Let me specialize this to S1. So if this is S1, so just one dimensional target, I can have a maybe phi squared minus phi. Well, I'll do it like this. this sigma model, I can now gauge the isometry of S1. So this would be an angle along the S1, right? So I can gauge that isometry, meaning that I will gauge the shifts of phi because they're just angles around the circle. So I'll end up producing this Lagrangian. And then the extra Lagrange multiplier I was talking about, that will just make sure that the connection is flat, right? So I'll add this inside the Abelian connection. So I'll introduce this term. Are people okay with this notation? It's just I'm using double plus and double minus to denote light-phone coordinates. It's just right. It's just two indices. Instead of using plus and minus, it's beneficial when we pass the supersymmetric because these have different R charge, Lorentz charge than the super spinorial indices. So that's the notation. But yeah, if you don't like it, just imagine that this is plus and this is minus, and then it's fine. Right. So this would be the gauged model. That's the parent action I was talking about. You see that's phi a and phi tilde. Right, and then if you integrate out, so you see that if you integrate out phi tilde, it will tell you that this is flat, right? So I can locally write a then as some lambda plus and minus lambda, put it in there and redefine my field phi, and I would end up reproducing the same model down here. But what happens if I should have had some coupling in front here, just in front of this term? So if I do something, if I first integrate out phi tilde now, I can actually pass to the dual model where I end up just having phi tilde as a dynamic variable. And after this is done, you can it's quadratic 3 different Lagrangian. You can just do that by hand. And what you find in that setup is that you end up with Lagrangian which looks the same like that, but with small difference, and that is that there will be 1 over R in front. So that is now interpreted as a dual circle, right? So if this is moving on the circle of radius R, this will be moving on the circle of radius 1 over R. So the T-duality is kind of strange, right? It connects two different geometries, and yet the model is same in a sense that if you quantize it and find the Hamiltonian, the spectrum is the same. So the quantum model is equivalent. And yet the target space geometry could be entirely different. Right, so that's the T-duality. And so now you kind of, you might wonder, so people wondered for longest time if there's a way to sort of geometrize the T-duality, right? So the way you would do that would be somehow put these two models together and think of some big space to begin with. So there's an attempt to geometrize this. And many people tried that and succeeded. And in bosonic situation, it's a well-known story and probably best understood by in Howell's papers. There's Howell's papers. So how do you do that? You first somehow overcome this parent action. Oh, you somehow start here by you omit this connection bit. So you first have an action which has not the original target space as its target space, but you double it. So now you have a model where you have some maybe fat M, right? So you have this fat M as a target space, and in principle, if I went back to my simple model with S1, it would be basically S1 times S1 dual. So maybe S1 with radius R and S1 with radius 1 over R. So I put together the dual and normal space, right? And there's some action for this model, and then the t-duality here is just some rotation of inside the space. So in this kind of model, I've geometrized the t-duality into the rotation in the target space in my sigma model, and that sigma model has a nice form. If I just put it on here, it would be. I'm going to explain very quickly what those objects are. Right. So that sigma model is very pretty. It looks almost the same, you know, if you compare it to the general sigma model. I'll write the general sigma model downstairs. In normal sigma model, right, there's a coupling to a target space metric. In the double sigma model, there's coupling to target space channels metric. That's the natural substitute for this guy in the doubled space. Right? So this is space. This space is doubled now, and you have this metric as a natural metric on that space, and you have this model, and then it's not the full story. There's constraints. It's supplemented with constraints, and those constraints are the following. They are some sort of solvability constraints. So how do they look like? They are following. So these are vector constraints. They're kind of, you know, you can to give you something to relate to. If I had a what do you want to say? If I had a model like this, just scalar field, then this constraint is something like self-duality. So it's as if I studied scalar field such that it obeys this kind of equation. Right? It's very reminiscent of that, and it actually can be, you know, put into form essentially. It just has this extra thing, but it's basically self-duality because if you square this guy, it's +1, so it works perfectly. So it's really like a model of self-dual scalars, but there's double amount of them, and if you solve for either one of the self-duality constraints, so there's plus and minus, you either get the original model or the dual model. But you can, yeah, it's all encompassed in this one model discovered by Paul, right? So that's the t-duality and the way to sort of approach it from the perspective of model with double target. Okay. Is this clear? I'm just like sketching the ideas behind. Not much of a me coming in just yet. All right, cool. Okay, so that's one thing. So this is cool. This is cool way to phrase the t-duality and the model itself in the double language. And the second, so that's one way you can generalize that original model to describe t-duality nicely. Another thing is that you can start adding supersymmetric, and so what I mean by that is that I start with some sigma 2, right, the same source, and if so, now I can imagine having more fields, right? I not only have the matter fields, but I also have maybe fermions or some other fields. They might have some supersymmetric in here, right? So if that happens, and if I can actually rewrite that model in 1.1 language, so I can, instead of working with these normal fields phi, I can pass to 1.1 description. 1.1 description is something where I substitute the bosonic worldsheet by superspace, right? So I have super Riemann surface with 2 bosonic directions and 2 fermionic directions, and so my field here would be some super field phi going to the target space, And the action looks almost the same, actually. It's really just this. Right, so it's something like this. The way to pass, and of course the integral over the bosonic directions as well. So very easily, you can integrate out these betas, right? I guess people know how to work with these objects, right? You just replace this with derivatives, and you act on your Lagrangian, and then off you get your bosonic model out of it, right?
Why do you replace with one?
Oh, that's just the prescription for Grassmannian integrals. I just know that the differentiation and integration is pretty much the same. So I can the way to treat it is that I replace that integral by derivatives, and then I distribute them over to my super Lagrangian, and after that I set all the thetas to 0. Right? That's the prescription. I mean, it could be made more fancy, schmancy, mathematically correct, but that's how you do it, really. And then you obtain the right supersymmetric model with supersymmetric model manifestly interpret. The advantage of this is that if I can cast my model in this form, I can very easily say just on the face value that it does have 1.1 supersymmetry, right? So that's the advantage of superspace formalism. But and so now we started wondering, if there is a good generalization of Hull's model to 1.1 superspace description, because I mean that's a natural question, right? That I need at least minimal supersymmetry for superstrings in RMS formalism, and it's nice to have this T-duality manifest description. So merging those two concepts together is quite nice, and indeed there's no obstruction, to be honest. Like this, you can probably, if you listen to me for the past 10 minutes, you can probably guess what the Hull model for 1.1 superspace is. You just make these fields fat, and you replace this cheap by H, and that's job's done, right? So I can just write it for completeness, but it's pretty clear. And of course, it's supplemented by those self-duality constraints, again, as I described before. So that's fun. But now more fun comes in when you start extending that worldsheet superspace into some extended superspace. So what I mean by that is that I want you to consider what happens when what needs to happen when I want more supersymmetries, right? Not just 2 here, but maybe 4. That would be the 2,2 case. And that's that's very old subject of people studying when does the 1.1 model uplift to 2,2, and I should briefly sketch what it's about. And this is very old story by fathers of superspace, Gates, Hull, Rochek, and Ricard von Unge, and all these people who studied the superspace very thoroughly. So what's happening here? So if so imagine I first start with the 1.1, and I can ask myself when do I have another extra supersymmetry which is not manifested in the 1.1 description. So the way to study that, the original supersymmetry would be something where I just apply my superderivatives, right? This is the 1.1 supersymmetry, but I can have it more, and so people would write an ansatz. This is how they derive their results and so index, right? So I better measure those indices, but I sneaked in some extra meters here. So this is an ansatz for the second supersymmetry, realized linearly. And now I can ask myself, so this would be, well, this is 3, 2,2. It's not in 2,2 superspace, but it's 2,2 supersymmetry, right? It has 4 supersymmetries, right? There's one for left and right here, and there's a second one for left and right here, right? So it's 4. And I'm now asking myself, when is this really real, you know, when is this really 2,2 superalgebra realized on my scalar fields or scalar superfields? And it turns out, the beautiful thing turns out, so you know, you need to do a lot of calculations, meaning that you want some relations to be obeyed, for instance, that these two commute with each other, these two different sets of supersymmetries, and they square to translations, right? So if you do that, it turns out that just, you know, miraculous thing happens. This tensor J, it turns out to be squaring to -1, or it needs to square to -1 in order for 2,2 to be satisfied, offshore. And then the second thing is that it satisfies this equation, so the mean point tensor of J is 0. So then you immediately, you know, and that really just comes off the closeness of superalgebra. And so you recognize this to be the target space complex structure. Right?
Sorry, what's the second one that you wrote down?
Oh, that's the mean point tensor.
Ah,
right?
okay, okay.
So it's some integrability for J. It basically, I don't remember it off the top of my head, but basically what it tells you is that if you construct these projectors, right, call them I plus minus, then you want to make sure that if I project something to plus direction of the and do the commutator and project to minus direction, this is 0, right? So you're making sure that the holomorphic and anti-holomorphic distributions in your tangent space are integrable. Right? That's what mean-point tensor tells you. And then you know that you can find these holomorphic coordinates, and then your manifold, your target manifold becomes complex, right? So that's a pretty thing. So you discover these constraints just out of closeness of superalgebra. That's very nice. It tells you that the target space has a complex structure. So in other words, you know, to phrase it geometrically, this model will admit extended 2,2 supersymmetry if the target is complex, and it's even more than just complex. It's actually keller, because there's some compatibility with the metric, right? So it becomes keller. What does that mean? That the target, you know, it's equipped with G and this complex structure, right? But such that G is some symplectic form and it's closed, right? So if that target space is scalar, then you can write that model in terms of the 2,2 superspace. I'll get to it, but
so even these the Keller conditions come from asking that the 2,2 supersymmetry is really there.
Yes, but for that I need to go at the level of Lagrangian. So I need to vary my Lagrangian and verify it's a it's a supersymmetry of the Lagrangian. Here it was just closeness. Yeah, but yeah, that's a good point. I should have made. Right. So this is purely from kinematic data that I have the complex structure, and this is coming from dynamics because that's where the G enters in the Lagrangian, not in the super transformations. Cool. Okay. Right. And now, so now you can do more stuff actually, and so people realized so I have this color geometry, and I can now I can now do some slight generalization, which actually yields interesting class of examples. So you see that there's these left and right supersymmetries here, and I can actually have different complex structures, maybe, or just two different tensors in my original ansatz, right? So I did some restriction at the beginning, right? I had just one J, but now I can have different J for left movers and different J for right movers. And it turns out that this also can close. I mean, obviously it closes if it's the same J plus the same as J minus, but there's more options. There's more options. And they yield some interesting geometries, which has been studied by mathematicians before, but then they just popped up, you know, very naturally in this supersymmetric setup, and so there was quite surprise. And what happens there? So what happens is that I get two tensors, plus and minus, which both square to minus one, and they form some interesting type of geometry. I won't talk about all the different situations, but so what happens here is that I can always construct this J plus, omega plus, and minus. So I can construct these two complex structures. They are no longer closed, but there's some condition on them to that some combination of them is closed, but not themselves independently. And there's some subclasses of examples you might recognize. So altogether, these geometries are called generalized Keller. And there are some subclasses which you might recognize. So first, there's a subclass of geometries which are, well, just Keller geometries. Right, Keller is when J plus is equal to J minus and omega plus is equal to omega minus, and they're closed. Right. There's another class which fits right in, and that's the hyperkeller. Hyperkeller, you know that J plus times J minus will be some other, I don't know, J3, some third complex structure, and they all give rise to some symplectic form, well, to some two forms, and they all together form this hyperkeller geometry. And there's another special class which I'll be mostly interested in, and that's the build class. So this is Parahermitian local product spaces, and there what happens is that it's very important is that those two complex structures commute. So if those two complex structures commute, that will be useful later on as to what we can do with it. But if they commute, it's called build, and yeah, we'll use it for some construction. And basically, so yeah, so this is the story. You can learn more about it from the papers if you're interested. I can provide you with references. But what's important is that this stuff has been studied by mathematicians from different perspectives, in generalized geometry. And what people realize is the following: that I can take this ugly data of omegas and j's. Like, it's a lot of data, and it satisfies some strange, integrability relations, and it's not very nice to be casted down. I can certainly recall that off the top of my head. But you can use this language of generalized geometry, right? You can take Tm plus T dual n, right? So this will be my generalized tangent space, and I can now study complex, so-called generalized complex structures, because everything's on the generalized tangent space. I can study generalized complex structures on this space, meaning they are just some endomorphisms of this bundle, right? And with square to -1, right? So I'll call these J plus minus, I'll call these j, right? And they square to minus 1. Okay, and it turns out, like, you know, that there's class of these which actually encode the data of these types of geometries, or generalized color geometries. And maybe that's like the one formula I should really write down, because it's absolutely crucial. And the formula is the following. Right, so what I just wrote down is a set of two generalized complex structures. And you see, I mean, there's also more complex structures, the generalized complex structures you can write down. But if I give you this data of generalized Keller geometry, you can construct these two guys, right? I mean, it contains the same data. It contains J. Oh shit! I was using I, and now I'm using J. So let me call these J. They are the same guys as I was working on. Right? If I give you this data, you can construct this generalized complex structure, and it turns out that they square to minus 1. They commute with each other. That's absolutely crucial. That regardless of what type of geometry you have here, like most of the differentiation here was based on as to whether those two complex structures commute or not commute with each other. If they don't commute, they create more complicated geometry in a sense. So I'll talk more about it later. But these, when you construct this huge guy, they always commute. So this J plus and J minus, script J plus, script J minus, they always commute. So that's a crucial ingredient for what will come later. And also what turns out is that if you take product of them, they give you generalized metric, and which is again endomorphism of T into Tn, and it squares to 1 this time, right? So that's what generalized metric is. And this stuff is like nicely connected to right. So this is what you get. So in particular, you know, you can see, for instance, that if you know, just to give you some flavor of for this formulas, if J plus, if J plus is equal to J minus, right, then you're in the Keller realm, and you see that the J plus would be just J transpose, and J minus would be right. Okay, so you'll get these two, and you see that if you multiply, so they both square to minus 1. One of them contains data about the complex structure, second one contains data about the symplectic form. If you multiply them together, you see that you get the generalized metric in the target, right? And right, you multiply them and you get H being G as G inverse G. And same holds here. There's just this H will be more ugly. It contains B field as well. In Keller geometry, you have no B field. Right. Okay. Is this clear?
Yes.
Yes. Okay.
maybe I have one little question. What differs in our ansatz which lead to generalized Keller structure, or sorry, generalized complex structure, as opposed to our former ansatz when we ended up only with a complex structure?
Oh, this is no connection to my sigma model just yet. This is just on a side that you can take all these data, you know, from the sigma model analysis and then put them in this generalized geometry framework. I'm not saying it has any relation to sigma model just yet. Okay, but I'm just saying, you know, it nicely repackages the data of the generalized Keller geometry. Does that answer the question, or?
I'm not sure. Maybe I ask it in another way. We set up some ansatz on the very left part of the blackboard, which lead us under some assumption of closeness of our supersymmetry algebra to J satisfying some relations which can be translated as to have a complex structure on our target, right?
Yes.
And then we made some other ansatz which allowed us to have J plus and J minus.
Mm-hmm.
But it didn't follow from the original ansatz.
True.
Am I right?
That's true. Yeah, I mean, this is mysterious right now. There's no way to, I don't know, derive this from the sigma model here. Okay, it's just a way to repackage stuff for now. It came from a different perspective from generalized geometry studied by Hitchin and Gualtieri, and to me, to my knowledge, I don't think they even, maybe they knew about those papers, but they didn't really, I don't know, derive it based on the sigma model story.
Okay. Mm-hmm.
Okay. But what's also nice, I should have mentioned that there are some, you know, some integrability relations for these objects, right? Because as I phrase it now, you know, you see that it squares to -1, that somehow limits the squaring of these guys to -1. But what about the integrability condition? And there's a similar condition here for J plus and J minus, which is the generalized integrability. So you can also rephrase everything in terms of that. If you don't use so if you use the same formula, right, for the projectors, but you just use Courant bracket, right? So if you use Courant bracket, you get the generalized integrability. And for instance, for Keller, if you study Courant integrability for this guy, you get that the omega is closed. So you really get your Keller geometry. And so it's just a nicer way to phrase stuff.
Okay, right. Thanks.
Okay, right. So what is the okay. Okay, so now what is the problem? First, what is the problem in the with these 2,2 models? So if I want to write stuff in 2,2 model, what does that mean? I want to have my source to be Q4 superspace, and so now I won't have just Z and Z bar. I'll also have X theta plus and theta minus, and theta plus maybe 1, 2, theta plus theta minus 2. Okay. I'll have more super coordinates, but somehow they already, even though it's a world cheap data, if I want to construct those supersymmetries out of these objects, I already have to know something about the complex structure in the target space. So what I mean by that is that if I want to construct a 2,2 superspace, I need these, I need plus minus and the bar plus minus. And how do they act actually? So D plus, I should write that out. So D plus would act in the following way. So this is not usually written out, but it's crucial to understand the structure of the superspace. Right. So these are my supersymmetric. Oh no, wait, what did I do? Plus minus here, right? Plus minus. For left and right movers, it's the different G plus J minus, and then it's the either barred or unbarred one that's this sign, right? So maybe I should so this plus refers to this being homomorphic. This is the minus, right? And these pluses minuses are based on the left and right, Cool. Okay. So that's something. And then but I really need this wouldn't nicely this wouldn't work nicely. So I need to actually pass to complex coordinates where these formulas become slightly more familiar maybe. So if I pass the complex coordinates, meaning that I diagonalize my J, which I can do because my instance are 0. I can certainly diagonalize one or the second one, but if they don't commute with each other, I can diagonalize both. So let me focus first on the Bell case. So in the Bell case, that's exactly the one where J plus and J minus commute with each other, and they both are Nguyen is integrable. So I can pass to the complex coordinates, and then I end up producing these. These superderivatives, right, or aligned with the complex structure, right? But what I wanted to say is that if you want to write things in terms of the 2,2 superspace, you're already incorporating in those complex structures and finding the accommodated coordinates to the complex structures, and that might not be even possible if you're in most generalized Keller geometry, because there J plus and J minus do not commute, and you can find the full set of nice coordinates which diagonalize both the J plus and J minus. And so let me first say what it is for build. So in build case, so in build case, it turns out that that was exactly the group I've chosen. Right? It's the one where J plus J minus commute. And then if you diagonalize them, it turns out that there will be a couple of i's and then minus i's in the diagonal basis, and then this will be my J plus. J minus will be such that it has a extra subdivision. There is extra subdivision here, where it's just i's in the first vector and minus i's and i's. So you see that there's parts like here and here where those complex structures are the same in left and right sector, and there's parts where they differ by sign, right? And for that reason, you're led to describe your geometry in terms of, or describe your sigma model in terms of two types of constraint fields. One of them is called chiral, and that is superfield of 2,2 type, which is filled by d bar, and the other one is called the twisted keller. And it looks like this. So twisted because it's not deep, both D bars, but one is D bar and one is D, right? For left and right, it's different. So you can, and really the idea is that in the blocks where the left and right complex structures do agree, those directions correspond to chiral fields, and the ones where they differ by a sign, they're described by these twisted keller fields. Right. So in particular, if you're in the case of keller geometry, the left and right complex structures will be exactly the same, and then you just need the keller fields to describe the whole geometry. So that's a special set, right? And then so when you have this. Now I'm slowly getting to the motivation for what we are studying after our coffee. Great. So if you have keller geometry, it turns out you only need these keller fields. Maybe n of them if your curve is n-dimensional, and the model will be just described by one function. Like fluid dynamics is hidden in this one function, keller potential, and if you reduce it down to your 1,1 superspace, or even down to bosonic superspace, sorry, in bosonic space, you end up reproducing the usual model, with 2,2 supersymmetry, right? So this is pretty concise form of the model. You have just one function which governs all the dynamics of the model. In build case, it's almost the same, because you were able to diagonalize both left and right complex structures, and then the same thing happens here. It's just with some other function which both contains phi and phi's. Okay. But so this is called generalized keller potential, and again, it's a function out of which, if you reduce to 1,1 superspace or down to bosonic space, you can just extract all your metric and complex structure, symplectic forms and everything, right? It just has full knowledge about the geometry of the target, right? So you know that you probably know, if you know stuff about keller geometry, you know this already, right? That the full keller geometry, even though it's a lot of data, it's G and J and omega, they are actually all described by this keller potential, which is not really a function. It has some ambiguity. You can add like keller. Should be precise here. It depends on both phi and phi bar, right? But if you add to it some function of just phi or function of just phi bar, it would be the same dynamics. So it's described by this function up to these transformations. So I guess you can think of it as some section of some log line bundle, or I don't know. There's probably some right words to call that. But anyhow, like that's the story. And now basically, but then beyond build, so once the J plus and J minus do not commute, you're a little screwed, and that people knew for the longest time that you're a little screwed, because you cannot really diagonalize both J plus and J minus at the same time, and those two, that condition was important to introduce those chiral and twisted chiral fields, and to write down model in such a nice concise form. You need more fields with some extra Lagrange multipliers included, and semi-chiral fields, and don't want to get into that. But here it's just not that nice. As here in Delph and Keller. Okay, but then you have this whole thing here, right? You know about this story, which I told you, and you immediately starting, you know, like, oh, okay, but if the whole problem is with this j plus and j minus non-commuting, then maybe if I pass to some double description, I have these fully commuting objects, and maybe I can get away with this problem if I double my space. So basically, the motivation was to, well, motivation was twofold. For me, the motivation was always this, you know, so I came from different background than my collaborators, and the motivation was that this is not pretty, and I know that this might make it work. So maybe if we double the 2,2 target manifold, we can somehow overcome the problem. So that's one motivation for why to double something and have 2,2 supersymmetric. Second motivation, which came from my collaborators, was more like how does the T-duality really work? And because we can also do T-duality in 2,2 superspace, that's one whole story. But how does it, you know, work nicely together with doubling of the target? And what is really the 2,2 description of Hall's model? Because Hall model is nicely described in bosonic case and in 1.1 superspace, but in 2,2 no one really knew what's happening. And so I can tell you that we don't have all the answers, but so answer for my question is non-existent just yet. Answer for their thing is not fully answered either, but we have at least some partial progress, and that's in the build case with isometries. So in the build case with isometries, and that's what I'll show you, and then I'll probably stop talking because I don't really have much time. And maybe comment on how we might progress further. So if I specialize the build case, so that's, you know, that's a little cheating because I already told you, oh, this is kind of worked out already. So why would I even double there, right? So if I wanted to answer my wondering, you know, there's no problem at this point already. But for just doubling for sake of doubling and comparing to Hall's model, it's a good question as any. So if I have this model with isometries, so what how do these have, and there are special isometries. Remember that for T-duality we needed those isometries in the target, right? Unless you go into some more general type of dualities. But if you have isometries along all the directions, so now we have a sigma model 2 into target. And you have isometries here, which say this is n-dimensional, and I have n isometries here, n isometries. If I have that, I can create this bigger model now, and the bigger model is the following. I can actually so the way you go, so the isometries first, they tell you the following, that your model actually looks like this. Maybe I'll just call it B here, B1, or oh no, B, just B. No. Right, so you see, so this is the statement about isometries, that your generalized keller potential does not depend on phi's and phi to us in general way, but in these combinations, meaning that it doesn't really depend on the imaginary part of either phi or chi, right? So if this happens, I can now define this new object, which will be the which I'll call B1. That will be something where I keep the first factor, and I'll construct this. So this is new keller potential where I dualized in chi and chi tilde. What I mean by dualized is that I did the Legendre transformation with all these slots, and I substituted in the keller fields like that. Okay. So right, I mean, if I have a function, I can find the Legendre dual, right? So here I just took this function and found the Legendre dual in the remaining class n coordinates, and the first ones were intact. This is this guy, and it turns out in 2,2 superspace, if you do that, if it originally depended on twisted chiral fields, these will be chiral fields. So that's something what people knew for the longest time. And now, if I can also do I can also construct second B, where I dualize in the first slot, and I have these guys. Right. So I can construct these two potentials, and if I now put them, so you see that I started with two types of fields, phi and chi, and they're complex conjugates. And now I have more fields, right? I have not phi and chi, but I have phi, chi, phi tilde, and chi tilde, right? So I've doubled my set of fields, right? So it's very, it's already reminiscent of what we expected to have if we double the target. So to even write down this thing, I need double the amount of fields. And now I can write down a model where I have this fat V, which depends on chi, phi and chi, and phi tilde and chi tilde. And they're complex conjugates, I'm not sorry. Right. And the fat V is really V1 plus V2. Okay. So this is the way to construct general doubled potential. That's what we call it, doubled potential for built geometry with isometries. Right? So if you do this, you have manifestly T-dual description of built geometry with the doubled target. So I claim that this is that would need some verification, but I claim that this model we've constructed, that is right 2,2 analog of Hall's model in 2,2 superspace, and but that one was supplemented by constraints, and those constraints are also to be found here, and they are very pretty. They just tell you that you're actually they tell you that what do they tell you? That if I they are connected to something, so I'll explain. Okay. So those constraints, what they tell you is that if I take derivative with respect to the second slot, those tilde coordinates are exactly equal to the second the derivative of the first potential, and same for chi tildes. They will give you the constraint on chi tilde guys with the derivatives of the second bit of potential with respect to the first slot. So it's a little complicated, but there's some logic in it. Especially it has some geometry behind that. We have now this doubled target space with two generalized complex structures on it, and these equations, so you can think of V as some generating function, and this describes some Lagrangian subspace in the double target space. So it's that's the original self-duality constraint. So now you have some double target, and it turns out that the original self-duality constraint just tells you now, if you restrict yourself to this Lagrangian subspace in the target space, then you end up producing one of the models. And there's two ways to resolve that constraint. You either go down to your phi and chi, or you totally switch the coordinates and you write everything in terms of phi tilde and chi tilde, and you produce the dual of this model. So the dual would be in terms of only phi tilde and chi tilde, and the v will be the Legendre dual of this function. But now we have this thing, and you know, it's manifestly the dual. It reduces. So if I reduce down to the 1.1 superspace, this produces the subdual constraint. And this gives rise to Hall model. In 1.1 superspace, which was obvious. So that's the partial result. Why is it useful? I mean, aside of putting stuff together, like marrying the 2,2 supersymmetry with generalized geometry for double field theory, it's useful to describe some special type of models. So you know that you have these models where if you do multiple d-dualities linked after each other, you might end up having some non-geometric background, right? And if you try to write down some Keller potential for these non-geometric backgrounds, it kind of fails. It's not really a nice function. But if you use this prescription for doubled doubled model, you can actually write down sensible doubled potentials, which are nicely behaving functions as they are normally in the geometric background. So what is the maybe conclusion? So it's useful, you know, to have no geometric backgrounds. So I'm saying, right? I'm saying that in this double description, we have a nice generalized color potential. It's useful to just describe, you know, geometrizing. For that you need those isometries, so that's the restriction. But now there's just more open questions than we've happened to answer at the beginning. So for instance, like, can we? So now I'll pass to the open questions we're wondering about. So how does this work in generalized Keller? Generalized Keller geometry is not known, still not known. Meaning how I overcome the case where I'm actually starting with two non-commuting complex structures. Although there is partial success in that department as well, because if I start with Bill, it turns out that I can double, and then I can do some T-duality where I'm brought to the frame where I actually produce two non-commuting complex structures in the physical space. So we can start with the build geometry, do the doubling, and then produce model where I actually have need for these more general constraint fields. So there's some partial progress. Build to more general. Right. So that's one thing we want to understand better. We also hope that there's actually some doubling possible without isometries. I think we now have some solid understanding how that should work by like revisiting old papers of Ricard von Unge and collaborators, where they actually use this extra doubling to overcome the problem with the semi-chiral fields. So I won't say more about that unless you ask me. And that's pretty much. I think that's pretty much it. I think I'll stop here. Right? Past the overtime anyway. So.
No. Okay, but thank you very much.
Thank you.
Thanks.
I have some questions.
Okay.
So where do I want to start first? So you mostly focus on doubling the tangent space with cotangent space, or do you really double also the coordinates of target space?
No, that's an excellent question, actually. Yeah. So this was all just motivation, but what we're actually doing is that we're working. So this would be working at the level of generalized geometry, but we're actually when we double stuff, we're doubling the coordinates. That's true. So really, what ends up happening is that you make this model, and then it's more like this Born geometry kind of thing. So like this is double model, so double the number of coordinates. You construct tangent space of this, and then after choosing a section and the section is really that self-duality constraint, one of iterate one or what. If you then you can identify it with the physical section, and there will be TM plus T dual M over it. So yeah, but it's the doubling of coordinates actually, not just of the tangent directions. Although we kind of know how to do that as well, how to just double the tangent directions. You can add some auxiliary fields to your original Lagrangian and just describe, in terms of the original fields, you can just add the tangent directions and sort of incorporate the generalized geometry data in that picture. And that has been known by other authors before, by Sapsi and some other people I forgot.
Is the self-duality constraint the same as what is called the strong section constraint?
Yes.
Okay, so projecting.
Although, well, yes and no, because it's in slightly it's the same thing, but in slightly different context, right? Here, I'm working with the sigma model, and if I quantize that, what was the self-duality constraint will play a role of strong constraint on those target space effective fields, right? So there the fields would depend on the coordinates here, and I would need some constraint to cut down the dependence on the dual coordinates, and they will come from quantizing that self-duality constraint I have on my sigma model, right? But this is like a first quantized description of the DFT, if you will.
Okay. Maybe I also wanted to ask more about this keller potential in the doubled case, because I got lost a little bit with all the fields and the
Right. Yeah, it's a little confusing. There's a lot of like technology coming in. So what is the yeah, so what do
I think it might be still in the other
right. So I mean the fact that there is some Keller potential that I don't know if I can describe any better in a couple of minutes, but I can describe the dualization maybe. I can. So what I mean by constructing the doubled Keller potential is maybe most transparent in the Keller base. So if I have a function, I can construct it the dual of me, which will be just dx minus 3x, right? Where I make sure that x. Sorry, Yeah, that's right. That's how I construct it. That's how this is the usual Legendre dual, right? So I start with a function and then construct this guy, and I solve for x's in terms of t's, right? So I also support this by this function, right? So if then I can solve this for x's, plug it in, and I have a function of t, right? So I do the same thing for that keller potential. But I mean, you can imagine if you have, another ingredient which was coming in is that if I have more x's, I can Legendre dual in some and leave the other intact, right? So there was the whole thing there. That if I have a built geometry, I first take those twisted chiral directions, I do the Legendre dual, and I end up producing some partial Legendre dual potential, and I can do it in the complementary way and sum them together. That is how it works. But yeah, in principle, for instance, for keller geometry, if I had a keller potential, I can fully Legendre transform, and I can just put these two together, and that would be my dual description. It's just that the chirals and twisted chirals are treated slightly differently. That's why it was a little complicated. But right, the thing is that this Legendre that has been known from the old literature. Like if you do the T duality in Ducomate superspace along the isometries aligned with the complex structures, you actually are describing the model by, if it was described by chiral fields, it's now described by twisted chiral fields. So chirals and twisted chirals are somehow T-dual with each other, if you will, and the new keller potential would be the double potential. The dual potential, Legendre dual potential. So we're just extending this and making some geometric, drawing some geometric conclusion about it. That's all. That's basically what's all behind it. It's kind of all pretty much known. It's just different perspective on stuff. Right.
Then I would just like to ask a bit more about the non-geometric backgrounds. So you've already wrote potentials of those.
Yes. So we have some model with I don't really know much of the literature on geometric backgrounds, but we have some model where we have three torus and with some non-trivial B field which is 2,2 supersymmetric. So it's a three torus with a fibered over line, and then it has some non-trivial B field. We can write down the keller potential for this, right? So in other words, we have 2,2 description. If you do 2T dualities on this model, because it has two isometries, then you end up producing some new keller potential, which is pretty much, which has the same problem as the metric and B field in those non-geometric backgrounds. Namely, it's not really periodic, right? In those tori directions. So it's kind of ugly. It's not really well-defined function, right, on torus. But it turns out that if you double that, so you go to this non-geometric background, you have some B which is supposed to describe the geometric, but it's a function, right? It's not a function on torus. But if you double it, if you introduce the double part by this procedure, because it's actually both geometry, you can double it, you can put them together, and those ugly bits from the first guy and ugly bits from the dual guy, they just cancel out. So we have nice description of this non-geometric background in Ducomate language. For that one model, I mean, I don't know that if there's some general conclusion you can make, but studying model by model, there it nicely works and resolves the issue with non-existence of the keller potential.
But you started with torus, three torus over a fiber over a line, and the line has a 2,2 supersymmetry.
No, the full model, right? That's the target, right? So I mean, like, I start with a model where I have some sigma, and here is the T3. times R, right? So I'm saying that this model has some, this is the target, so there will be 4 fields, and I can find some isometries and dualize with respect to that. The isometries along the cycles of the torus. And then that new background I end up with is non-geometric, but if I should double everything, I don't really know what the double space is in terms of like global topology, but if I double it, I end up producing doubled model which has a sensible double potential in terms of like right in terms of like the right periodicity conditions.
Yeah, one more. So in double field theory, where people always thinking of doubling the target space by exactly doubling the same space, or just I don't know, writing some manifold which has double the amount of dimensions.
Yeah, no, doubling is maybe a confusing word exactly for this reason what you just pointed out, because that space might, so first of all, even for the simplest case which I showed at the beginning, it wasn't just the same space doubled, right? It was the circle and circle with the different radius,
yes.
right? So it might happen that, so for torus generally, if it will be torus with some radii, the dual torus would be the radii with the inverted, right? So it's not the same space, but it might even happen that the double space will be somehow, so it might not even be globally product actually.
Okay.
Right? So it's even worse. So it might be something what's locally, so people talk about this in this Born geometry literature, like it's something what locally has the differentiation of coordinates to axis and x tilde, but it globally might have some non-trivial structure. So it's this local product space. But to be honest, we haven't really, that being physical paper, we didn't really care much about the global structure here. We just are trying to construct some sigma models, and I don't know, maybe some of them don't even have a global understanding or global meaning. So we were a little naive and cavalier in that direction.
Hirschi, do you have questions?
Maybe at this point I haven't, because you pretty much covered some of mine. But yeah, very impressive talk. Thanks, Ondra.
Yeah.
All right.
So
Because it's recorded, I maybe will have one other watch.
Yeah,
and
you can just
ask
talk to me
questions afterwards.
I think we have email or Facebook on each other, right? So
Yeah.
goodness. So thank you, Ondra, and thanks, Hirschi, for being here. And
Yeah. Thank you for giving me such opportunity to watch nice talk in the pre-Christmas time.
yeah.
And
Okay, I will stop now.